Next, we want to describe planes in space. To describe a plane, we'll give a point P0 on the plane along with a vector n, which is orthogonal to the plane. So n is for normal. We call this the normal vector to the plane. Then if we have any other point in the plane, we'll call it q, the vector from P0 to q will be contained in this plane and therefore orthogonal to the normal vector. And this is an if and only if. So a point is contained in the plane if and only if its vector from P0 is orthogonal to the normal vector. So if and only if its dot product with the normal vector is 0. Now, so we call this the vector form of the equation defining this plane. Now explicitly, if our point P0 has coordinates x0, y0, z0, and the normal vector n has coordinates a, b, and c, then this expands out to the equations a times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. And we could also rearrange this to have all the variables on one side and all the constants on the other. So we call either of these second forms the component form of the equation. The latter form is very useful because 2 points or 2 planes with the same a, b, and c coefficients, but different d values, will be parallel. So here's an example. Find an equation for the plane through the point 1, 0, 1, perpendicular to the vector negative I plus 3j minus k. So we're going to write down the equation in the form ax minus x0 plus b y minus y0 plus c z minus z0 is equal to 0. So our values here, that's going to be, tell us that negative x minus 1 plus 3y minus z minus 1 is equal to 0. And now if we bring the constants to the other side, then we get the equation negative x plus 3y minus z is equal to negative 2. Although it won't be part of this course, I'll also show you, so this is an implicit form, formula or equation defining the plane. I'll show you how to get also a parametric description. So basically we'll just let y, or x and y, take on the value of variables, and then we can solve for z as z will be negative s plus 3t plus 2. So this form, the first form, makes it easy to check if a point is on the plane. The second form makes it easy to produce examples of points which are on the plane. So here, s and t are any real numbers. Another very useful way to describe a plane is that any 3 points, which are not collinear, so not all on the same line, uniquely determine a plane. So how do we go from a description like this to an equation of our form? Well, we already have a point on the plane, so that's good. But then we need a vector which is orthogonal to it. So our way for producing orthogonal vectors is the cross product. So if I imagine these 3 points, I'll define vectors u and v as b minus a and c minus a. So these vectors both lie in the plane, and so they are both going to be orthogonal to the normal vector we're looking for. So b minus a, that's 2, 0, 1. C minus a is 3, 2, negative 2. And so u cross v is I, J, K. 2, 0, 1, 3, 2, negative 2. So that's negative 2i, then negative 4, negative 3, plus 7j, and then plus 4k. So this gives us, this is what we take to be our normal vector. So now the equation becomes negative 2x plus 1 plus 7y plus 4z minus 1 is equal to 0, or negative 2x plus 7y plus 4z is equal to 4 minus 2 is equal to 6. Next, what about finding a line given a point on the line and a plane to which the line is perpendicular? So this is the plane x plus 2y minus z equals 4. We're looking for a line that is orthogonal to this plane. But being orthogonal to this plane will mean that it is a multiple of one of the any normal vector for this plane. And by this form of the equation, we can see that one choice of normal vector is I plus 2j minus k. So we combine that with the point we're given, and so we get that a parameterization of the line will be 2 plus t, x equals 2 plus t, y equals 2t, and z equals negative 3 minus t, for t a real number. Finally, what about a plane that goes through a given point and is parallel to some other plane? Well, we can see from here that the normal vector for the other plane is 1, negative 3, 1. And so if this plane is parallel, it's going to have that same normal vector. And so now we just plug in the different p0. And so we get that x plus 1 minus 3 y minus 1 plus z minus 3 is equal to 0. And then we just move things over. So x minus 3y plus z is equal to, so that's 3, another 3, and so negative 1.